Okay, now in your syllabus, you will also need to learn about EM waves. EM waves in IGCSE, you already learned before. What you're learning now is basically a rehash of what you've learned with some additional things. Okay, now electromagnetic waves are just transverse waves that travel through space without a need for a medium to carry them. I mentioned this in the first lesson last week. EM waves are transverse waves. They don't need a medium. And usually EM waves are actually made out of electric fields and magnetic fields that are oscillating at right angles to each other. Now, what makes an EM wave, where we tell you it is oscillating electric field and magnetic fields oscillating at right angles to each other, this is not important in your syllabus, all right? So don't worry about this because AS, you don't learn electric field and magnetic field yet. So if we just say that EM waves is actually just oscillating electric and magnetic fields that are oscillating at right angles to each other, just take it as it is. You don't really need to bother so much about it, okay? Now, EM waves travel in a straight line with a constant velocity in a vacuum regardless of their frequency. Just now I mentioned to you, for any waves that travel in the same medium, it doesn't matter what the frequency is. As long as the wave is still the same, their frequency different won't do anything. The speed will always be the same, okay? Now for EM waves that travel in a vacuum, they will always travel with a particular constant velocity known as the speed of light. C equals to 3 times 10 power 8 meter per second. Okay, so this value here, you will use a lot. Every time you see EM waves being involved in the question, you need to automatically assume the speed as 3 times 10 power 8. Okay, they won't tell you the value of the EM's wave speed. You're supposed to know that speed by heart. Okay, and then another thing we'll tell you here is that since EM wave is a transverse wave, it may be polarized, made to oscillate in only one plane perpendicular to the direction of travel. Polarization you haven't learned yet. This one is actually a new addition to your syllabus. We will cover this next week. So this one you may not understand this one yet. Okay, but the important thing that you just need to know for now is that for EM wave spectrum, you need to know what are the constituent waves inside the spectrum. You remember it as radio waves, microwave, infrared, visible light, ultraviolet, X-ray, and gamma rays. Okay. Now, last time in IGCSE, it's probably just sufficient to know the order of these waves. But in your syllabus right now, in addition to knowing the order of these EM waves, you are required to know roughly the order of magnitude of the wavelengths. Okay. Order of magnitude normally refers to the power of 10. When I say order of magnitude, it normally refers to the power of 10. How many power is it? Okay. So you need to know how to reproduce the EM wave spectrum along with their correct order of magnitudes. So this one here is your EM wave spectrum. All right. In your AS syllabus, your paper 1, the MCQ question, confirm there will always be 1 or 2 questions that makes use of your knowledge of the EM wave spectrum. Okay. If you cannot recall the EM wave spectrum, you cannot answer those questions. So usually in your paper 1, there will always be 1 or 2 questions that requires you to recall the EM wave spectrum and answer from there. Okay. So how do you recall the EM wave spectrum? How do you reproduce the EM wave spectrum? Usually there are a few steps. Okay, this one is the step that I find to be the most efficient. What you will usually do, the step is actually listed in the next page, is that you normally draw a series of vertical lines first, which is this one. Okay, you draw a series of vertical lines first, and then you start from the left side with 10 power 3. Okay, you start from the left with 10 power 3. And then as you go towards the right, you must decrease by 10 power 3 for each line. So 10 power 3 to 10 power 0 to 10 power minus 3 to 10 power minus 6 to 10 power minus 9, 10 power 12, 10 power minus 15. Okay, now there's an exception here. Between 10 power 6 and 10 power minus 9, between these two, you need to insert 10 power minus 7. Now the 10 power minus 7 here is actually for visible light. Okay, the wavelength of visible light, you need to remember it as between 400 to 700 nanometer. Okay, the easy way to remember this value 400 to 700 is you just remember this now. Usually you need to go to school by 7 a.m. and you can only leave school by 4 p.m. So it's 4 and 7. So if you remember this related to the time that you always go to school and come back from school, you should be able to remember it as 4 and 7. Okay, so the wavelength of visible light is between 400 to 700 nanometer. You change it to meter, you will notice that you have a 10 power minus 7 here. That's where this 10 power minus 7 came in. Okay, and wavelength of visible light, it consists of 7 different colors. You need to know the arrangement of those 7 different colors. The easy way to remember it is by remembering it as the name of a person, Roy G. Biff. Okay, and then going towards the right, the wavelength decreases. So 400 nanometer would actually be for violet light because this is the smallest. 700 nanometer would be for this one, for red light. Okay, between a range of 400 to 7, the smallest one will be violet, the largest one will be red. Okay, so you need to remember this. Your paper 2 sometimes would require, paper 1 and paper 2 sometimes would require you to know this in order to answer the question. Okay, so once you have drawn the vertical lines and fill in the spaces, once you have drawn the vertical lines and fill in the numbers, you try to fill in the spaces in between. Okay, it's R, M, I, V, U, X, G. Okay, so there's a phrase that is sometimes useful to remember. Raging Martians invade Venus using X-ray guns. So the first letter of each word represents that wave. Okay, so your other teachers may use a different phrase. All right, usually people try to relate it to a phrase to remember it easily. For me, I usually use this phrase. Okay, so first letter of each word represents the wave type: radio waves, microwaves, infrared, visible light, ultraviolet, X-ray, and gamma rays. Okay, so going towards the right is where wavelength decreases. All these values that you see here represent the order of magnitude of the wavelength. Okay, so that's for this. Now, if you wanted to calculate out the frequency, going towards the left is where lambda decreases. You can also say that going towards the right is where the lambda decreases. You can also say that going towards the right is where frequency increase, because frequency is inversely proportional to wavelength. So when lambda decrease, frequency increases. Okay, so if you want to say calculate out certain values of frequency for a particular wave type, you can normally do it by using V equals to F lambda, because you know the wavelengths from here. You also know that the speed of any EM radiation is 3 times 10 power 8 meter per second. So let's just say if I say V is equals to F lambda, I want to find out roughly the frequency of X-ray. So 10 power minus 9, 10 power minus 12, a middle value is 10 power minus 10, right? So 3 times 10 power 8 for the speed, 10 times 10 power minus 10 for the wavelength, 10 times 10 power minus 10 for the wavelength, I will be able to get the frequency from here now. So it will be 3 times 10 power 8 divided by 10 power minus negative 10. You will get 3 times 10 power 18 hertz. Okay, so this will allow you to find out what is an associated frequency. So it's really important to remember this. a lot of questions that you do later on will be based on your ability to recall the spectrum. Okay. So the method to remember it is what I just wrote here. You might have an easier method, but this is the method I always tend to use. Okay, so if that one is okay, maybe I just show you one or two questions that talk about how to use the EM wave spectrum. Okay, all right, okay, just look back at page 1. All right, there was one question that we did not do. An electromagnetic wave has a wavelength that is numerically of the same order of magnitude as the diameter of a nucleus. So same order of magnitude here, I mentioned it refers to the power of 10. Okay. It is numerically same order of magnitude as the diameter of a nucleus. Now, diameter of a nucleus is roughly 10 power minus 15 meter. This one is actually part of your estimation for chapter 1. In chapter 1, you probably learn something about estimating values. This one is actually covered under estimation of values. Diameter of a nucleus is roughly 10 power minus 15 meter. So what they want you to do right now is find out which EM radiation, which EM wave has the same order of magnitude as the diameter of a nucleus. So you see, like what you have now, you cannot do this question without knowing what are the values of all the EM waves. So in your case here, to be able to proceed, you need to know, you need to reproduce back the EM wave spectrum. So I'll just show you how I do it. So in my case, if I want to reproduce the EM wave spectrum, just draw a series of vertical lines, then start from 10 power 3, decrease by 10 power 3 each time. So you get 10 power 0, 10 power minus 3, 10 power minus 6, 10 power minus 9, 10 power minus 12. Always remember that between 10 power minus 6 and 10 power minus 9, there is a 10 power minus 7 because of visible light. Then raging Martians invade Venus using X-ray gun. This is your EM wave spectrum. So you want to find something that has 10 power minus 15. Okay. Right. So 10 power minus 15 should be gamma rays already. Wait, I missed one line here. Negative 9, negative 12, negative 15. Okay, raging Martians in Venus using X-ray gun. So the only wave here that seems to have order of magnitude for the wavelength that's up to 10 power minus 15 is gamma rays. Okay, so this is how you can do it in one way. All right, so this is just one example of that. They ask you which region of the EM spectrum does the wave occur. It will be gamma rays. Okay, so let's go through another one. Maybe this time in page 5. Okay, page 5. Okay, page 5 is this one. All right, so page 5, questions 27. Page 5, question 27. Okay. So now you have P, there's a source emitting infrared radiation, and Q is a source emitting ultraviolet radiation. The figures in the table are suggested values for the wavelengths emitted by P and Q. Which row here is correct? So again, you see this one, you can't plug values out of thin air. You can't just simply pull out a value out of thin air. You have to remember the EM wave spectrum. You reproduce by the EM wave spectrum. Only then can you see clearly which one is which. They want you to select infrared and UV. Okay. So from the graph that you have, for the EM wave spectrum that has been reproduced here, I know infrared is here. I know ultraviolet is here. Okay. So I know infrared is between 10 power minus 3 to 10 power minus 6 meter. The wavelength of UV is between 10 power minus 7 to 10 power minus 9 meter. So you look at your answer choices, which one seems to be hitting the range? So P is infrared, right? Q is UV. So you look at answer choice A, 10 power minus 5 is within this range, but UV is 10 power minus 8. It's also within this range. So answer by right should be A. But let's just try and do for the other subsequent answer choices just to be sure. If you look at answer choice B, 10 power minus 5 is within the infrared range, but 10 power minus 10 is already out of the UV range. So this one is the wrong one. Okay. And then you look at answer choice C and D. Infrared, they say is 10 power minus 7. This is already clearly out of the range. So it's correct to say that A is the answer now. Okay, so this one is 1. Then maybe we just do one more question, page 11. Okay, page 11, question 23. Page 11, question 23. Okay, so let me just get rid of that. Okay, which electromagnetic waves have the wavelengths of 10 power minus 2 meter, 10 power minus 1 meter, 10 power minus 10 meter, and 10 power minus 13 meter? So again, you just look at the EM wave spectrum. You reproduce by the EM wave spectrum when you practice reproducing your EM wave spectrum, and then you just look at it. Okay. So 10 power minus 2 meter, where do you suppose it is at? It is actually going to be, maybe I use a different color. I use orange now. 10 power minus 2 is here. 10 power minus 5 is here. 10 power minus 10 is actually here. And then 10 power minus 13 is actually here. So it should be microwave, infrared, X-ray, and gamma ray. So it will be answer choice B, like this. So on the same page, I think there was another one. Question 22 and question 24. Yeah. Okay, last one. On the same page, question 24. Each of the principal radiations of EM spectrum has a range of wavelengths. Which wavelength is correctly linked to its radiation? So what you do is you look at each of the associated radiation. Gamma ray is 10 power minus 9. Gamma ray is here. It is not 10 power minus 9. Out. Microwave is 10 power minus 5. Microwave is here. It's 10 power minus 5. It's not within the range. When I say range, you're looking at between these two. It's 10 power 0 to 10 power minus 3. For gamma, it was 10 power minus 12 to 10 power minus 15. So microwave is not inside here. This is out. Let's look at ultraviolet. Ultraviolet is here. It's between 10 power minus 7 and 10 power minus 9. But you're looking at 10 power 8. This is again out. So last one, look at X-ray. X-ray is here between 10 power minus 9 and 10 power minus 12. Okay, so 10 power minus 14 is also not in. So something is wrong here. I think this one should have been the answer. Oh, okay, sorry. I did a mistake here, right? C is ultraviolet. I know it's here. The range is between 10 power minus 7 to 10 power minus 9. I'm having 10 power minus 8. It is within this range. Sorry. So answer is C. Okay, right? So notice here, out of the few questions that we've done, a lot of them really just relies on you reproducing, being able to reproduce the EM wave spectrum. Once you're able to reproduce the EM wave spectrum, it is quite straightforward to answer the question. So that's why I mentioned to you, it is very important to know how to reproduce it, because for sure, in paper one, there will always be at least one. Sometimes it can go up to 3. So it's something like a bonus mark question if you are well prepared for it. Now, under the wave section, there will be one particular chapter that there will be one particular subtopic that is called Doppler effect. Now, Doppler effect is actually the apparent change in observed frequency due to relative motion between source and observer. Okay. Now, what it means here is something like this. Let me just try to play for you a video. Okay, just give me a second. I try to play the video here and show you what it is. All right. So a Doppler effect can normally be seen, for example, from a fire truck or an ambulance where the siren is blaring. What you will notice is that if, let's just say, you're standing stationary and then you notice a fire truck or ambulance going towards you, you will notice that the frequency of that ambulance or fire truck changes. And then after that, when the fire truck or ambulance goes away from you, you will notice that the frequency again changes. So that change in frequency that you perceive to have happened is actually what is known as Doppler effect. So to give you a better idea of what it is, let me just share with you a video. Okay. All right. So this video here will show you a fire truck that is approaching the observer. Okay. Notice what happens to the sound of that fire truck when the fire truck approaches the observer and moves away from the observer. Okay, so I'll just start playing the video here. All right, so hopefully you can hear the sound. I'll play the video. So I'll play the video again one last time. Okay, right. So from what you can hear, you notice that that fire truck, as the fire truck approaches the observer and then moves away from the observer, the frequency somehow changed. You can actually hear a very clear difference in the changes. So that is what we call as Doppler effect. Right, there's an apparent change in the observed frequency because of relative motion between the source and the observer. In your case, the observer is actually the person taking the video. The source is actually the object that is making the sound. In this case, it was the fire truck. All right, so it is usually produced whenever you have relative motion between source and observer. Okay, So Doppler effect is observed whenever a source of waves is moving with respect to an observer. Okay, so there are two main cases whenever there's relative motion between source and observer. The first case would be when your source is moving towards observer, and another one is when source is moving away from observer. So if I tell you you have an observer here, the fire truck could be moving towards the observer, or it could be moving away from the observer. So under these two cases, the frequency that you observe from that fire truck would vary. So what we'll tell you is that when the source is moving towards the observer, you will notice that there's an apparent upward shift in frequency for the observer towards whom the source is approaching. In other words, your observed frequency is larger than your source frequency, F naught more than Fs. So it could be that maybe the fire truck is emitting sound of frequency 100 Hertz. But what you think you heard for the frequency of the fire truck was that you probably heard it as 150 Hertz. So there's a difference in what you hear and what the source is actually producing. So you perceive the observed frequency to be higher here for the case where your source is moving towards observer. Now, if you go to the other case where the fire truck passes through observer and is now moving away from the observer, what we'll tell you is that there will be an apparent downward shift in frequency for the observer from whom the source is moving away from. What this means is that your observed frequency is less than your source frequency. So if you look back at the fire truck itself did not change the frequency of sound that it emits. It was always at this frequency. But for the case where the fire truck was moving away, this time, since the truck is moving away from the observer, the frequency that this person observes will be less than the source frequency. Maybe he will perceive it as being 50 Hertz. Okay, so this one is moving towards the observer. This one is moving away from the observer. Okay, so you could have two different observed frequencies depending on whether the source was moving towards the observer or away from the observer in the first place. Now, throughout this motion here, there's actually no change in the frequency of the source. Okay, the fire truck itself that you see here, as it was moving towards the observer and as it was moving away from the observer, the frequency did not change at all. The fire truck did not purposely change the frequency as it approached the observer or when it moved away from the observer. They did not purposely change its frequency. It's just that the observer somehow perceived there was a change in frequency. Okay, right? So that is what Doppler effect actually means. Now, there will be a particular equation that will be used to calculate observed frequency. That one is this one, where we tell you F naught is equals to VW over VW plus minus Vs times Fs. Okay, where F naught is observed frequency, Fs is source frequency, Vw is the speed of the wave, Vs is the speed of the source. Okay, so observed frequency and source frequency, this one probably you can understand it very well. Now, what do we mean by the speed of the wave and what do we mean by the speed of the source? Say, for example, if I talk to you about the fire truck, it was emitting sound waves, okay? It was emitting sound waves. The sound wave that it emits has a certain speed. The wave itself has a speed. That is what we mean by the speed of the wave. So in my case, the speed of the wave, which is sound wave here, could be at 320 meters per second. But the source itself, which was the fire truck here, could be moving with another different speed. It could be that this fire truck was moving with a speed of 35 meter per second. All right. So there's actually two different speeds most of the time. The speed with which the source is moving and the speed with which your wave is moving. Okay, so that's why you have VW and VS here. One is speed of source, one is speed of wave. All right. Okay, then one last thing to kind of mention to you here is that in general, when you have a higher speed of your source, it tends to result in higher changes in observed frequency. Okay, the faster you move towards the person or the faster you move away from the person, it will result in a higher change in observed frequency. Okay, this one we'll talk about it more in the next page. All right. Okay, now Doppler effect can be observed for all types of wave. Right, it can be observed for any type of wave. Doesn't matter whether it's transverse wave, longitudinal wave, doesn't matter whether it's water wave, sound wave, or light wave. It can be observed for all wave types. All right. So there are two prominent examples of Doppler effect. The first one is actually something that I just illustrated to you. When you have an ambulance that travels towards a bystander, as the ambulance approach with the sirens blasting, the pitch of the siren, which is normally due to the frequency, was high. But then after the ambulance moves away, the pitch of the siren was low. So this one is actually a similar example, but this time they're using an ambulance. So my case here was that I have an observer and this ambulance is my source. So as the source moves towards the observer, what happened was that the observed frequency is higher. Observed frequency is more than the source frequency itself. But when the ambulance move away from the observer, the observed frequency is lower. The observed frequency will be less than your source frequency. Okay, so this was the example that I just illustrated to you. Now, another example of Doppler effect could be when you're trying to see the EM radiation emitted by stars. Okay, so electromagnetic radiation emitted by stars in a distant galaxy would appear to be shifted downward in frequency if the star is moving in the direction that is away from the Earth. On the other hand, there will be an upward shift in frequency if the star is moving in the direction towards the Earth. So what it means from here is something like this. Let me just rub off certain things. What it means here is something like this. Say, for example, this is the Earth. Okay, and then you have a star right over here. The star emits EM radiation of a certain frequency. Okay, so if you have an observer here on Earth and he picks up that EM radiation, he ought to be able to determine the frequency of that EM radiation. But now what we're telling you is that the star could be moving away from the Earth or towards the Earth itself. So in cases where the star is moving away from the Earth, this one is moving away, the observed frequency is observed to have increased. But if the star is moving towards the Earth, the observed frequency would be observed to be lower. Okay, so that's what this one is saying. If you notice that the star frequency, the observed frequency from the star somehow increased, that means the star is moving away from you. Or it somehow decreased, that means it's moving towards you. Okay, now they make mention of these things here where they say if it's moving away from the Earth, sorry, I think I did a mistake here. If the star was moving away from your Earth, the frequency is dropping. Sorry, my mistake. On the other hand, if the star was moving towards the Earth, the frequency will be increasing. Sorry, I kind of mistook that. Because this one star is your source, it moves towards your Earth, the frequency ought to increase. And then your star, if it moves away from the Earth, is moving away from the observer, so the frequency should be less. Okay, sorry, I got the thing mixed up just now. Okay, now for the case where the star is moving away from the Earth, the frequency observed will be less. We say that you will have something called redshift. Okay, why do we call the frequency as having a redshift? Is something like this. If you remember the color spectrum of visible light, where we tell you you have 7 different colors, Roy G. Beef, and then we say going towards the right is where wavelength decreases. Now, when you went towards the right, the wavelength decreases. At the same time, the frequency is increasing because wavelength is always inversely proportional to frequency. Because of this, V equals to F lambda, V being constant would mean that lambda is inversely proportional to frequency. So over here, if you're going towards the right, your wavelength is decreasing. This in turn will cause your frequency to increase. So here, if my wavelength drop, my frequency ought to be increasing. So right now, for the case when you're moving away from the Earth, your frequency is increasing. It should be going the other way around. This is where we tell you your frequency is increasing. Okay, let me just wipe this one off because this is confusing. Okay, if you're moving away from the Earth, your frequency is shifted downwards. You're actually moving towards the left. Okay, now when you're moving towards the left, so that your frequency decreases, sorry, this one is frequency decrease. If you're moving towards the left so that your frequency decrease, notice that you're moving towards the red colored side of your visible spectrum. That's why we would say that if your source is moving away from if your star is moving away from the Earth, there's a downward shift in frequency, you're experiencing a red shift because you're moving more towards the red side of the visible spectrum. Because when you move towards the red side of the visible spectrum, that is where your frequency is dropping. Okay, so conversely, if we say that your star is moving towards the Earth, towards the observer, you will have a upward shift in frequency. You will have an increase in frequency. So you are experiencing a blue shift. Okay, blue shift here, you will notice if my frequency is increasing, I'm going towards the right, I'm actually approaching this blue color here. That's why here we will say that you're experiencing a blue shift. You're moving more towards the blue colored side of your visible spectrum so that you're having an increase in frequency. So that's what red shift and blue shift actually means. All right, it's just another way of telling you whether the frequency is increasing or decreasing. Okay, so this is for that. Okay, then I move on to a more specific example of the source moving towards observer and source moving away from the observer. All right, so I'll just clear off whatever I have here. Now, just now I did mention to you that when your source is moving towards the observer, you will say that the observed frequency is larger than the source frequency. Okay, so what I could say is that maybe this one was moving at 30 meters per second. All right, and then this source is emitting sound waves of a certain frequency, where the frequency was maybe 100 hertz. Okay, So this sound wave itself has a speed of say 320 meter per second. Okay. Now, in the general case where your source is moving towards observer, observed frequency will always be larger than your source frequency. If you want to calculate out the observed frequency for the case where source is moving towards observer, you will generally use this F naught equals to VW divided by VW minus Vs times Fs. Just now the general form of the equation was F naught VW plus minus Vs times Fs. So whether it's going to be positive or negative depends on whether the source is moving towards the observer or away from the observer. In the case where it is moving towards observer, this one will be minus. All right. Now, an easy way to remember why this one would be a minus would be just to remember this important observation. F naught more than Fs. You see, if I say that source is moving towards observer and F naught is more than Fs, it could mean something like this. F naught is 1.2 of SF of Fs. Okay. Notice that this one is a fraction more than 1. If I say F naught is equals to 0.8 Fs, this one is not F naught more than Fs. This one is F naught less than Fs. Okay. If I say F naught equals to Fs, then it will be exactly like this. Okay. So this one is F naught less than Fs. This one is actually F naught equals to Fs itself. If I want to say F naught more than Fs, it could be something like this. Notice that this one is going to give you a fraction more than 1. Okay. So if it gives you a fraction more than 1, obviously the equation there that you have here, this one will be minus, because the way you look at it will be something like this. You see, the top portion is VW. The bottom portion is VW minus Vs. So obviously the bottom portion is going to be less than the above, right? See, VW, the over VW minus Vs. The original VW itself is being subtracted another different value. So the bottom value is going to be less. So if the bottom value is going to be less than the top, obviously you're going to get a fraction more than 1. Maybe I better just write it here. So if you have this one is going to be less than above. Therefore, you're going to get a fraction more than 1. Okay, so then you get this one. F naught is more than Fs. That's how I usually would remember whether it's going to be positive or negative. If I see F naught more than Fs, that means I should get a fraction more than 1. So the bottom portion must be minus, so that the bottom value is less than above. If the top value is more than below, I'm going to get a fraction more than 1. Okay, so this one is for this. Now, this one is just for a case where your source is moving at a particular speed. There will be cases where we tell you your source is moving towards the observer, but it could be speeding up when approaching the observer, or it could be slowing down when approaching the observer. So what happens then to the frequency increase? So what we could tell you here is that if say it was speeding up, so say right now, if it was moving at a speed of 30 meters per second before this, the source frequency is 100 hertz. My observed frequency is say maybe 120 hertz now. Okay. What if for the case that the source is speeding towards the observer? If the source is speeding towards the observer, let's just say it's speeding up, the speed now becomes say 45 meters per second. All right. What then would happen to the observed frequency? the observed frequency that you get ought to be higher. It could be maybe now 150 hertz. Okay. Because you see, if the original source frequency is 100 hertz, right now at the speed of 30 meters per second, I'm getting an observed frequency of 120 hertz. This one is showing me that I have an increase in frequency of plus 20 hertz. But when I'm speeding up, say right now I'm moving with a speed higher than before, maybe say it's now moving at 45 meters per second, my observed frequency is going to be larger. So if you compare this with the original source frequency, this one you notice is plus 50 hertz. The increase is larger. But what if right now the source is moving towards the observer, but you are slowing down? So if say you are slowing down, maybe I go and do some other location. Say if you're slowing down, right? Say you're slowing down. Maybe you are moving with a slower speed of 15 meters per second. So if you're moving with a lower speed of 15 meters per second, your observed frequency would still be higher than the source, but it won't be as high as before. It could be that maybe this one is just going to be 110 hertz. Okay, so you're still having a frequency larger than your source, but it's not as large as before. So this one, what you see here is that when you're slowing down, your frequency increase is smaller. Maybe it just increased by 10 hertz. Okay. So that's what these last two statements means. If your source is speeding up when approaching the observer, the frequency increase is generally larger. If the source is slowing down when approaching the observer, the frequency increase is smaller. So one way to look at it in the form of a graph, or in the form of a diagram, would be something like this. Say this line represents your frequency. Your observed frequency at the original speed v at 30 meters per second was this. If you're speeding up, so meaning to say your speed is now higher than v itself, maybe now you are at 45 meters per second, your frequency increase will be larger, represented by this line here. Okay, your original frequency is here. This one represents your source frequency. Okay, so if you were moving with speed v before this one represents your frequency increase. It was at 120 hertz. This one was plus 20 hertz. Okay, when you're speeding out, your speed is higher than v itself. You're moving at 45 meters per second. Your new observed frequency is 150 hertz. It is plus 50 hertz now. Okay. Then if let's just say you were slowing down when moving towards the observer, your speed is lower than the original v. Maybe now you are at 15 meters per second. Maybe now you're at 15 meters per second, giving you an observed frequency of 110 hertz. Your increase in frequency is just plus 10 hertz. Okay, so that's one way of looking at it. That's why in the previous page it was mentioned that a higher source speed tends to result in a higher change in observed frequency. You notice that the bigger your speed moving towards the observer, the bigger your increase. But if the lower your speed when moving towards your observer, the lower your increase in frequency. Okay, so this is for the case where you're moving towards observer. Okay, so that's for this. Okay, now let's just do one last final one. What about the case where the source is moving away from the observer? Okay, so this one, the reasoning or logic will be very similar. If the source is moving away from the observer, F naught will be less than Fs. So observed frequency would always be smaller than your source frequency. So in the case where observed frequency is smaller than your source frequency, you could say it as being something similar to this. F naught is 0.8 Fs. Okay, observed frequency less than Fs. It could give you maybe something like this, where we say that this fraction here is less than 1. Okay, so to find the observed frequency at a particular speed, this one will be F naught equals to VW divided by VW plus Vs times Fs. The previous one was minus. The current one is plus. Okay, if observed frequency is less than source frequency, you're always going to get a fraction less than 1. So this one by right ought to be plus. Because right now, same reasoning applies. At the top, you have VW. At the bottom, you have VW, the same VW plus VVS. So you're going to get a value that is more than the top. So this one, the value is larger than the top. Therefore, the fraction is less than 1. That's why I know this one will be plus. Okay, that's how I usually remember it. Okay, so same thing as before. If let's say my current source is moving with a speed of 30 meters per second, it had a frequency, source frequency of say 100 hertz. Okay, it has source frequency of 100 hertz. If it was moving with speed v itself, my observed frequency will be less than the source frequency. So say for example, my observed frequency is 70 hertz. Okay, so that one represented in this diagram here could be this. This one is my source frequency. When I'm moving with speed v, my observed frequency is going to be 70 hertz. Okay, my source frequency was originally 100 hertz. Okay, sorry, I better just remove this. This one was therefore fraction less than 1. Okay, so this one was the original source frequency, 100 hertz. So how much has my frequency decreased? This one has decreased by 30 hertz. Okay, so let's just say right now, same thing. My source is moving away from the observer, but it is speeding up and moving away from the observer. In your case here, the frequency decrease would be larger. So I could say that maybe your speed now is 45 meters per second, but now your observed frequency would be even lower than before. It could be that maybe this one is 50 hertz. So if you're moving with a speed, if you're speeding up, speed higher than before, your observed frequency would be lower. It could be that now this one is 50 hertz. Notice that between the original, the source frequency and the observed frequency, now you have minus 50 hertz. Okay, so maybe I write some values here. This one was 30 meters per second. This one was 45 meters per second, right? Okay, then the last one. You say right now your source is slowing down when moving away from the observer, the frequency decrease is by right going to be smaller. So right now, say maybe I have a velocity that is 15 meters per second. My observed frequency will be not as small, right? The frequency decrease won't be as large as before, it will be smaller. So maybe now my frequency is 90 hertz. Okay, so for the case where you're slowing down, when moving away from the observer, your speed now is lower than speed v. Okay, lower than your speed v, your frequency decrease is going to be smaller, right? You slow down when moving away from the observer, your speed now is lower than before. Maybe right now, rather than 30 meters per second, it is 15 meters per second. your frequency decrease won't be as large. You will still have frequency decrease, but it won't be as large. So maybe now it will be at 90 Hertz. Okay, so you see this one is still smaller than 100 Hertz, but it's not as small as compared to the other. This one just decreased by minus 10 Hertz. Okay, so again, this one again ties back with what you see here. A higher source speed results in a higher change in observed frequency. In your case here, a higher speed results in a larger drop in observed frequency. A lower speed when moving away results in a lower drop in observed frequency. Okay, so that is for Doppler effect. If I wanted to draw it for you, yeah, maybe that one I just leave it for some other time. But generally, this is the gist of it. Okay, so this is Doppler effect. Okay, so maybe we do some questions. All right, maybe we spend half an hour or so to do some of the questions for Doppler effect. Yeah, Doppler effect is actually quite a recent addition to your syllabus. You only see it from 2016 onwards. All right, this one is only from 2016 onwards. It's actually a recent addition to the syllabus. You only see from 2016 onwards. Before 2016, you won't see this question. All right. Okay, so if that is okay, let me just go through some Doppler effect questions for you just to reinforce what we've learned. Okay, can you just have a look at page 8? Okay, have a look at page 8 of the worksheet. Okay, page 8 of your worksheet, which is this one. All right. Now, with which types of waves can Doppler shift be observed? All right. Just now I mentioned to you, Doppler effect can occur for all types of waves. It doesn't matter whether it's transverse or longitudinal. It doesn't matter whether it's sound, water, light. It can occur for all types of waves. So this one, it will occur for all types of waves. All right. Then you look at the next question, question 21. You have a distant star that is receding from the Earth with a speed of this value. It emits light of frequency 4.57 times 10 power 14 Hertz. The speed of light is 3 times 10 power 8. Doppler effect formula can be used with light waves. What will be the frequency of this light when detected on Earth? So this one here, you notice that there is actually some sort of relative motion between observer and source. And they specifically mentioned Doppler effect here. They want you to calculate the frequency. This frequency is actually supposed to be your observed frequency. All right. Then after that, what is your source frequency? They say it emits light of frequency 4.57 times 10 power 14 Hertz. This is the frequency of the source. Okay. Then after that, there are also some other speeds that were listed here. The 1.4 times 10 power 7, this is the speed with which the star is receding from the Earth. This one is the speed of the source. The speed of light is 3 times 10 power 8. This is actually the speed of the wave. This is VW. Okay. When they say it's receding, this means that your source is moving away from the observer. Okay, so it could be that Earth is here, your star is here, it's moving away. Okay, so if it's moving away, the equation will be F naught. Sorry, wait now. If it's moving away, your observed frequency will be less than your source frequency. So F naught is going to be VW over VW plus VS times Fs. So from here, it's just really a matter of subbing the things in. Okay. Now you need to know the equation The straightforward answer, do you need to memorize this equation that I just written here? Yes. Okay. It will it will speed up your workings later on when you actually go for your exam. It's actually also given in your exam paper, in your data sheet, sorry, in your formula sheet. But it looks like this. Wait, let me open up one of the paper for you. Okay, why did I open the marking scheme? No, moment, let me see the question paper. Okay, yeah, let me just open one question paper. If you somehow forgot the Doppler effect equation, you can actually also refer to the equation inside your formula sheet. It's on the third page of your question paper usually. So they did give you the Doppler effect equation, but it's written in this form. Okay, it's actually the same as F naught equals to VW divided by VW plus minus Vs times Fs. Okay, they're the same. All right, it's just that this one seems to be written in a slightly different manner. Okay, so in the event that, let's say, you somehow forgot about the Doppler effect equation, you can always still refer to the equation itself on your formula sheet. But it's best to just memorize it. Okay, right. So back to this question. This one is just a simple matter of subbing in the values after using the equation, after applying the correct equation. VW is 3 times 10 power 8 divided by 3 times 10 power 8 plus with 1.4 times 10 power 7 multiply with 4.57 times 10 power E14. Okay, so you can just try and calculate it out. 3 times 10 power 8 plus 1.4 times 10 power 7. 3, 8, so 4.57 times 10 power 14. You should be getting 4.37 times 10 power 14. We should be answer B. Okay, so that one is for Doppler effect. The first part. This is the first time they started asking you Doppler effect questions. That's why you see it's pretty straightforward. But in the more recent years, you notice that they start to increase the difficulty. Okay, so this one is page 8. If you're okay with this, we'll move on to page 11. Okay, so I'll clear off everything here. Just move on to page 11. All right. Okay, so just move on to page 11 of your worksheet. Then look at question 23. Okay, so this one is some example again. You have a source of sound of frequency 1000 Hertz that moves away from an observer at a speed of 30 meters per second. The speed of sound is 330 meters per second. What is the frequency of sound heard by the observer? Okay, so this one, usually for Doppler effect questions, always try to identify whether the source is moving away or towards the observer. So this one I know is moving away. So therefore I know F naught is less than Fs. F naught is VW over VW plus Vs times Fs. So identify what are the variables. 1000 Hertz is Fs. Source of sound is moving at speed of 30 meters per second. This is Vs. Speed of sound is 330 meters per second. This is VW. Okay. So they want frequency of sound heard by the observer. They want F naught. Okay. So I think that's just a simple matter of subbing everything in again. VW is 330 divided by 330 plus with VS times with observed frequency 1000 Hertz. So you get 330 divided by 360 times 1000. You're gonna get 917 Hertz. So answer is 8. Right. So this one is okay. Then let's move to the next page, page 12. Okay, so if you're okay with that, just move on to page 12, question 24. All right. Now, what was mentioned here is that they told you there's a car traveling with constant velocity that passes a stationary observer. The observer hears a change in frequency of the sound emitted by the car. Which of these following statements is correct? Okay, so you already established that they just say that the traveling car passes a stationary observer. Okay, so they didn't really specifically mention whether it's moving towards or away, but here it can be implied as moving away. So let's just look at the answer choices one by one first. Okay, they say the change in frequency is greater as the car moves away than as it approaches. Okay, this one is actually wrong. Notice that they say the change in frequency is greater when you move away than you approach. Now, if I give you an observer here, and you have that car that moves towards the observer and moves away from the observer, notice that they told you that this thing is moving with constant velocity. It wasn't speeding up, it wasn't slowing down at all. It was still moving with constant velocity. So say V is 30 meter per second here, and then V is 30 meter per second here, right? And then I tell you that the observed frequency, the source frequency here is 100 Hertz. Source frequency is still 100 Hertz. We did not change anything. Now, if you're moving towards, okay, moving towards observer, your observed frequency will be higher. So I could say that maybe the observed frequency is 150 Hertz. There's an increase of plus 50 Hertz. But when your source, the same source, is moving away, okay, this one is moving away, your observed frequency will be less. Okay, your observed frequency will be less. But because your speed is the same, your change in frequency, your drop in frequency is actually going to be the same. It will be that maybe this one is 50 Hertz. If this one moving towards the observer, it experiences a change or an increase of 50 Hertz, with the same speed, when you're moving away, you should also be experiencing the same change in frequency. You should be experiencing a drop in frequency of the same magnitude. So this one you should be minusing 50 Hertz. Okay. The frequency change is the same because your speed was the same. Okay, so just now I mentioned to you, the speed of your source determines the change in frequency that you experience. If the speed did not change, your change in frequency won't change. But whether the change will be causing an increase or decrease depends on whether your source is moving towards or away. Okay, so first statement here is already wrong. Okay, because constant velocity would mean constant, sorry, maybe right here. Constant velocity would mean same change in frequency. Okay. Okay, and then you look at B. The greater the speed of the car, the greater the change in observed frequency. Yeah, this one was what I just mentioned, right? This one should be correct. The greater the change in your speed, sorry, the greater the speed of your car, the greater the speed of your source, the greater the change in observed frequency, the bigger the magnitude of your frequency change. But whether it's going to cause an increase in frequency or decrease in frequency depends on whether it was moving towards or away. Okay, so the correct statement here is actually supposed to be B. Okay, but we can still look at C and D also just to see what was wrong with them. Okay, the observed frequency is lower as the car moves towards observer and is higher as the car moves away from the observer. Okay, now this one is the wrong observation, right? When you move towards observer, your observed frequency is supposed to be higher. When you move away from the observer, your observed frequency should be lower. Okay, so this one is also wrong. Right? And then after that, the last one, they mentioned that the volume of sound heard by the observer does not change as the car approaches. This one wrong. It will change. Just now, the video that I played to you, you notice that the frequency, the pitch did change, right? The volume did change also. Okay. So the frequency does affect the volume. Okay. So because you understood that if your source is moving towards the observer and away from the observer, the frequency will change. Consequently, the volume should also change. All right. Here they say volume heard does not change. This one is wrong. It should change. Right. So this is for page 12. I move on to page 14. Okay. So this one is okay. I move on to page 14. Okay, page 14 is more on structured. Okay, so page 14, June 2016 P22. So we'll go through that. Okay, without open on the past here, I can't seem to find it. June 2016 P22. Question 4. Wait a minute, sorry. This one is 16P22. Question 4A. Oh, I skipped some of the stuff actually. Okay, if you look at the questions, they ask you by reference to the direction of propagation of energy, state what is meant by longitudinal wave and by transverse wave. You can just say that for longitudinal wave, the oscillation of particles are parallel to the direction of propagation of energy. Okay. Oscillations of particles are parallel to the direction of propagation of energy. Whereas for transverse waves, oscillation of particles are perpendicular to the direction of oscillation, to the direction of propagation of energy. Now notice that the question here asks you to refer by reference to direction of propagation of energy. So your answer must be related to the direction of propagation of energy. In the notes, longitudinal wave, I mentioned it as oscillation of particles are parallel to direction of wave travel. Transverse wave is where oscillation of particles are perpendicular to direction of wave travel, right? So if you replace the term parallel to direction of wave travel or perpendicular to direction of wave travel, you may not be marked as correct because the question specifically say you need to refer to direction of propagation of energy. So make sure you refer to that specifically. All right. I also mentioned to you that direction of propagation of energy is actually the same direction as your wave travel. They're actually the same thing. All right. Okay, so answer for question 4A, that one should be okay. All right. This one shouldn't be that big of an issue. Okay, now the next part we will be asking you about describe Doppler effect. So Doppler effect is the apparent change in frequency, is the change in the apparent frequency when the source is moving relative to the observer. Okay, so one keyword here is that you need to make mention of change in apparent frequency. Okay, because as now I mentioned to you, the frequency that you observe, you perceive it to have changed, but the frequency of the source itself did not actually change. When the source was moving towards you and away from you, they did not purposely change their frequency. It's just that you perceive the frequency to have changed. So there's a change in apparent frequency here. All right. So this one is the answer. Okay, then after that, you also have the next one, where they mention to you a distant star is moving away from an observer. State the effect of the motion on the light observed from this star. It was that same example just now I mentioned. If this is your Earth, this is your star, you move away, moving away, observed frequency will be less than source frequency. Okay, so frequency of light observed decreases. You can actually just make mention of one of these statements. There are actually 3 different statements here. 1, 2, 3. But you really only need to pick one because it's just worth 1 mark. You could also say that wavelength of light increases because just now I told you frequency is inversely proportional to wavelength. If this one you know that frequency drops means wavelength increase. That's why here we say wavelength increase. Okay. Or you could also say it this way. This one is actually the marking scheme answer. They say that the frequency and wavelength observed shifts towards the red end of the visible light spectrum is experiencing a red shift. This one I mentioned to you is because of this. You go towards the right, wavelength drop, frequency increase. You go towards the left, wavelength should increase, but frequency drop. So you're trying to go here towards the left. You're approaching the red end of your visible light spectrum. It's called redshift. Okay, so this one is for this. Okay, then after that, we move on to one example here. Okay, now a car travels at constant speed towards a stationary observer. The horn of the car sounds at the frequency of 510 Hz and the observer hears a frequency of 550 Hz. The speed of sound in the air is 340 meters per second. Calculate the speed of the car. Okay, this one changed a little already. Keyword here, towards observer. So towards observer, F0 more than Fs. So you're gonna get this, the one with the negative. So you can identify what are the parameters here. 510 Hz is the source frequency. 550 Hertz is the observed frequency. Speed of sound in air, 340 meters per second. This is the speed of the wave. So sub everything in, and you should be able to get the answer as 24.7 meter per second. All right. Okay, so you get the answer as 74 meter per second. Then after that, I think this is the end of this question already. Okay, so let me just go and see some other relevant questions here. You know, we done page 14. Okay. Maybe I have a look at page 16, right? Okay. The next one you could probably have a look at is page 16. And then after that, 74. Okay, right, let me just go through this. Let me just ask you this. Are you okay with Doppler effect right now? Do you need more examples in Doppler effect, or should I just give you the question so that you can do it as your homework? Then after that, you try it by yourself.
Yeah, you can just give me the questions as homework.
Okay, right. So what I just mentioned to you, all those are like the basics. Now you should have the basics patterned down already. So I think the later questions you just do as homework. All right. Otherwise, the questions will tend to become quite repetitive. All right. So you're okay with this, then maybe I go through polarization. All right. Polarization will probably take half an hour or so or less. Okay, so I'll give you the questions for Doppler effect later on. All right. That one you do as your homework. Then if nothing else, then maybe I do polarization for you. Okay. All right. So wait on. Let me just say something here first. Give me maybe 30 seconds. I need to go and search something.
Sure, no problem.
Okay. Right now, just give me 30 seconds. I need to go and find something from here.
This is a question about.
Wait, okay, no, I need that. Okay, found it. All right, so sorry for the delay. Okay, let's go back to the waves notes. All right, because I was trying to open some sort of animation to show polarization. Okay, right, let's go to page 9. Okay, for polarization. All right, now polarization, this one, it used to be in your syllabus before 2016. And then after that, they remove it between 2016 to 2021. And then after that, it's back in again from 2022 onwards. So they've been testing you polarization on and off. Before 2026, it was in, but between 2016 and 2021, they remove it. And now from 2022 onwards, they put it back in. All right. Okay. So polarization is actually pretty straightforward. Okay. So first thing first, we revisit some of the concepts that we've learned before. You remember that we said that transverse waves have displacements that are always perpendicular to the direction of wave travel. Okay, so what we'll tell you is that when you have transverse waves, the displacements are always perpendicular to the direction of wave travel, but the oscillations of these particles can happen in any plane perpendicular to the propagation direction. What we mean by that is this. If say I tell you that this one is my wave is moving in this direction, my particles could be oscillating up and down like this, okay, in this manner here, up and down. So it's oscillating in the vertical plane. But if I look at the horizontal plane like this, if my particles oscillate like this, left and right, rather than up and down, this one is also still considered to be transverse wave. Because strictly speaking, when you're talking about transverse wave, they only say that the displacement of the particles must be perpendicular to the direction of wave travel. So that alone could imply that your transverse wave can actually oscillate in different planes. So it could be oscillating in a vertical plane where it oscillates up and down, giving you something like this. This one is considered transverse wave. Or it could also be oscillating in a horizontal plane, oscillating left and right instead. Under both cases, you still consider to be transverse wave because oscillation of particles is still perpendicular to your wave travel. But horizontal plane and vertical plane is not the only plane that your particles can oscillate. It can also oscillate in a diagonal plane. So you can be oscillating in a diagonal plane like this, diagonal plane 1, or you could also be oscillating in another separate diagonal plane. This one say maybe diagonal plane 2. Okay, so transverse wave can oscillate in many different planes. All right, so there will be cases where you do not want the transverse wave to oscillate in so many different planes. You want them to oscillate in only one direction, only one plane of oscillation. Okay, so in order to make a transverse wave oscillate in only one plane of oscillation, or having the oscillation restricted to one direction, you will need to polarize the wave. Okay, when we say you polarize a transverse wave, it means you are actually restricting the oscillations to only one direction. You're restricting the oscillations to only one plane of oscillation. So once you restrict the oscillation to only one plane of oscillation, or oscillation to only one direction, it is still considered to be a transverse wave because the direction of oscillations is still perpendicular to the direction of propagation or energy transfer. Okay, so looking at it in the form of a diagram, your notes already have the diagrams to tell you what is the difference between unpolarized and polarized wave. This one here could be an example of unpolarized wave. Notice that they can oscillate in many different directions, in many different planes, while they're moving towards this direction. This is the direction of propagation. Your wave is moving towards the right, but your particles can be oscillating in any of these planes. So once you polarize the wave, your wave will only oscillate in one direction. It could be that it oscillates only in the vertical plane. In this case, we call it vertically polarized, or it can be made to oscillate in only the horizontal plane. In this case, we call it horizontally polarized. Okay. So this one is what polarization means in concept. Now, polarization can only be done for transverse wave. Okay, only transverse wave can be polarized. Longitudinal waves can never be polarized. Okay, this one is actually quite important to know. Longitudinal waves, like sound waves, can never be polarized because they always oscillate parallel to the direction of travel. Okay, so this one, if you look at transverse wave, just now I mentioned to you, they can oscillate in the vertical plane, horizontal plane, or even the diagonal plane like this, if you're talking about longitudinal, wave, if this is the direction of your wave travel, this is your wave direction, your longitudinal wave will only oscillate parallel to your direction of wave travel. There's actually no plane of oscillation to see because it always oscillates parallel to your direction of wave travel. So there's actually no plane of oscillation. Okay, for longitudinal wave, your oscillation of particles is always parallel to your wave direction of wave propagation. Okay, there's no plane of oscillations whatsoever, so you cannot really polarize anything. Okay, but it's different for transverse. Transverse, you know, is always perpendicular to wave travel. So because it's always perpendicular to wave travel, you end up having different planes of oscillation. So this one, you want to limit the oscillation, you want to limit the direction, you want to limit it to only one plane. So transverse wave can polarize, longitudinal cannot, because it oscillates parallel to the wave direction. There's no plane of oscillation in the first place. Okay, so transverse wave can be polarized. When you want to polarize a transverse wave, you will make use of something called a polarizer or polarizing filter. Okay, a polarizer is the thing that allows your wave to oscillate in only one certain direction. Because what it does is that it only allows oscillations in certain planes to go through, to be transmitted. So an idea for that, a concept for that could be something that is shown in this diagram here. So let me just clear out the diagram. So say for example, you have an unpolarized light. It oscillates in all the different possible directions, horizontal, vertical, and diagonal. You want it to be polarized so that it oscillates vertically, only in the vertical plane. So to do that, you need to put a polarizer in between. When your unpolarized light passes through your polarizer will only allow oscillations in a certain plane to pass through. In your case, you can think of the polarizer as having something like vertical slits here, so that if this wave tries to pass through the polarizer, only particles that are oscillating vertically can pass through. That's why you get this vertically polarized light here. The others that are oscillating in different directions like this, or like this, cannot pass through. So it doesn't get transmitted past the polarizer. All right. So if I look at this vertically polarized light again, all right, this vertically polarized light is over here. They brought it downwards. What if I go and take the vertically polarized light, and then this time I go and put another polarizer in its path, but this time I rotate it 90 degrees so that it only allows oscillation in the horizontal plane to pass through. So in my case here, because this one is vertical, but this one is horizontal, the directions don't match, so it cannot pass through. So you get nothing at the end. No light is transmitted. Okay. So when it comes to polarizers or polarizing filter, you normally see these little slits here. These are called your transmission axis. Okay, the transmission axis can be thought of as this. It determines the direction of oscillation of wave. Okay, the transmission axis actually determines the direction of oscillation of wave after passing through it, after passing through the polarizer. Okay, so you will hear this term quite often in your questions. the transmission axis. Just think of the transmission axis as being the thing that determines the direction of oscillation of wave after passing through the polarizer. Okay, one way you can think of is that the polarized wave will always oscillate parallel to the transmission axis. Okay, will always oscillate parallel to the transmission axis. Okay, so just think of it as this. All right, it determines the direction of oscillation of the wave after passing through the polarizer. After passing through the polarizer, any polarized wave will always oscillate parallel to that transmission axis. Okay, so light can also be polarized through reflection, refraction, or scattering. This one I don't think is that important. An example of polarization in everyday life is your polarized glasses. Right, it's actually talking about your sunglass. You notice that when you wear sunglasses, the glare from the sun is actually less. The reason for that is because your sunglass, the lens, is actually a type of polarizing filter. You can think of your sunlight as being similar to this. When you look outside at the sunlight, your sunlight is transverse wave because it's EM radiation. It consists of visible light. Okay, so that sunlight, or rather the visible light, is transverse wave, is unpolarized. It could oscillate in many different directions. But when you put on your sunglasses, your sunglass is actually the lens is made out of polarizing filter. So it only allows sunlight oscillating in a certain direction to pass through. So let's just say in this case, it only allows sunlight that's oscillating in the vertical direction to pass through. So only the vertical ones will pass through, but the other directions will not pass through. So in essence, you actually have less of the sunlight already. That's why you notice that the glare or the intensity of the sunlight is less. It's because your sunglasses is having a polarizing filter. It's actually helping you to filter off some of the sunlight by only allowing sunlight oscillating in a certain direction to pass through. Okay, so that one is what we mean by that. All right. Okay, now there's one thing here that I think I should mention to you also, now that I've gone through the concept of polarizer for you. Now, if you look back at that same page, page 10, okay, this is page 10. This one is unpolarized light. This one is a polarizer with the transmission axis vertical. This one you understood it as only the waves that are oscillating in the vertical direction can pass through. Okay, this one you understood it correctly. And then after that, if let's say you have a vertically polarized light like this, and then you have another polarizer rotated 90 degrees where the transmission axis is horizontal, this one is actually perpendicular to your polarized light. You understood that there is nothing here, nothing will pass through. Okay, and now let me just erase this. You understood that there's nothing that passes through. Now, what if I give you a separate case like this? Let's say I give you the same vertically polarized light, and then I give you another polarizer, but the polarizer is not having a transmission axis that is vertical nor horizontal. Let's just say right now the polarizer has a transmission axis that is at a certain angle. Say it looks like this. Say it makes an angle of theta. Say it makes an angle of theta. So if this one is polarized light that is vertical, and then you put a polarizer, okay, you have a polarizer where the transmission axis is actually at a certain angle theta, neither vertical, neither horizontal. In other words, not parallel or not perpendicular to your direction or polarized light. Now, it may be easy for you to assume that since this direction and these directions don't match, you might have thought that you get nothing because the directions don't match. But that is actually the wrong assumption here, the wrong understanding here. Okay. If let's just say you have a polarized light vertical like this, and then after that you have a polarizer with a transmission axis. Maybe I better write it here. Transmission axis at an angle that is neither parallel or perpendicular to direction of polarized light. Now, you may have thought that nothing will pass through because the direction doesn't match. Now, in cases like this is actually the wrong assumption. What will actually happen is that you will actually have polarization happening here. You will actually get the wave from here passing through, but it will be oscillating parallel to your transmission axis. It will be oscillating in the direction of your transmission axis. You will actually get that wave back. Okay. You will actually get back that wave. Okay. At that same angle. Okay. So you will get polarized light in the direction of transmission axis. But with reduced intensity. Okay, but with reduced intensity. All right. So what we mean by that is that, say right now, if your light here has an intensity I naught, it tries to pass through this polarizer here that has a transmission axis at a certain angle that's neither parallel or perpendicular. This polarized light will actually be polarized in this direction, in the direction of the transmission axis, but it will be with reduced intensity. Okay, so this is one thing that you need to somehow get it right first. Okay, now this observation can actually be explained using something called Malus law. That one is actually the next page. All right, now Malus law is completely new in your syllabus. All right, this is part of polarization, but it's completely new from 2020 onwards. Even before 2016, it was never asked. So this one is actually quite new. All right. So Malus law is used to explain a number of things. It's used to find the intensity of polarized light after passing through a polarizer. So just bear this, just remember this. Malus law is always used when you want to find the intensity of polarized light after passing through a polarizer. You must have a polarized light first, passing through a polarizer. The intensity of that polarized light after passing is explained using Malus law. Okay, so Malus law is only used for this. When you have a polarized light passing through a polarizer, it is used to find the intensity of the light after passing through the polarizer. Okay, so when you want to find the intensity of the polarized light after passing through the polarizer, it is given by this equation. I equals to I naught cos squared theta. Okay, where I is actually the intensity that is actually transmitted through. I naught is the original intensity, and then theta is the angle of your transmission axis. So this one here is actually your transmission axis. Is at angle theta. Okay, so based on this equation here, I is equals to I naught cos squared theta. You will see a few things. If the theta is 0, meaning to say it is parallel to transmission axis, meaning to say transmission axis parallel to polarized light, your I will be I naught cos 0, sorry, why do I keep writing theta? It will be cos 0. Cos 0 is 1. Okay, so you will get I equals to I naught. Okay, that one is actually referring to this case here in the previous sorry, not in the previous page. It wasn't listed here, but I can also still show you. If let's just say that you have a polarized, vertically polarized light like this, and then you have a polarizer where the transmission axis is also in the same direction, they're both parallel, you will get back that same polarized light. If this one is intensity I naught, this one will also be intensity I naught. Okay, that's what this one is trying to tell you. If your transmission axis is parallel to your polarized light, meaning you say both are vertical now, same direction. Once this polarized light passes through, you actually get back that same light. Okay, that's what this one means. Okay, but what if you have a case where your transmission x, your angle theta is 90 degrees? Let me just draw it here. Theta is say 90 degrees. That means your transmission axis is perpendicular to polarized light. So in this case, I will be I naught cos 90. Cos 90 is 0, so therefore I is 0. Okay, cos 90 is 0, cos 0 is 1. Okay, so this one is actually showing to you this case, the one that you see in the previous page. Okay, the one that you're seeing here, under page 10. Okay, this one is this case. All right, if your theta is 90 degrees, meaning to say your transmission axis is perpendicular to your polarized light, you don't get anything. That one is actually this case here. Notice that this one is the transmission axis, this is your polarized light. They're actually perpendicular to each other, so you're getting nothing here. Okay, Mellor's law will tell you that. Okay, now what about the case where you have nothing in what if the case you have neither 0 or 90 degrees, you have certain angles in between? All right, so in the case where your theta is neither 0 or neither 90, is between, let's just say your theta is between 0 and 90, your I will be between 0 and I naught. Okay, it'll be somewhere in between. If your angle is between 0 and 90, your intensity, resulting intensity, will be between 0 and I naught. Okay, so that is what this thing actually is talking about. All right, at any other angles, a portion of polarized light is still transmitted but with reduced intensity. This is the referring to this example here that I was just talking to you about. Okay, if let's just say your transmission axis is at an angle that's neither parallel or perpendicular, the polarized light that you have will still pass through, but with reduced intensity. It will oscillate in the direction of transmission axis, but with reduced intensity. Okay, you can actually also see this from a graph. Okay, so let me just clear off everything because it's getting quite messy. You can actually see this from a graph, because you see Mellor's law tells you that I is equals to I naught square, sorry, I naught square, is it? Yeah, not I naught. It's equals to I naught cos square theta. Notice that this is a squared cos function. So if you were to plot a graph of I versus theta, you're gonna get a cos square graph. like this. Okay. If you get a cos graph, cos theta graph, it tends to look like this. But if you get a cos square graph, it will be squared. So you get something like this. Okay, this is what you learn from maths. So because this one is a squared term, it will look like this. Now, at 0, as I mentioned to you, that is where you get I naught. I is I naught. I is equals to I naught. At 90, I is equals to 0. Okay, so any angles between 0 and 90 would give you values between 0 and I naught. Okay, that's what we meant from that. All right. Okay, so Malus law, just like I mentioned to you specifically, is only when you have polarized light passing through a polarizer. The equation is only applicable for that, where you have polarized light passing through a polarizer. In the event that you do not have a polarized light, instead you have a unpolarized light instead. Okay, in the event that you have an unpolarized light and you pass it through a polarizer, what we'll say is that the resulting intensity will always be half the original intensity. So if you have a polarizer here and you have unpolarized light like this, it will still pass through. Only the waves that in the direction of transmission axis can pass through, but the intensity will always be half of the original. Okay, it will be half. Okay, there's no calculations involved whatsoever. You just need to know that if it's unpolarized light passing through a polarizer, you only get half. That's all there is to it. But if it's polarized light passing through a polarizer, you actually need to calculate it from this. Okay, so before I kind of end the lesson, let me just show you the polarizer thing. Okay, now you should be able to see this. All right, this little thing that I've just shown here. Wait out. Okay. Two slits. One slit. Okay, right. So before I end the lesson, let me just show you some simple simulation or polarizer. Okay, so say right now, this one is my polarizer. Okay, you notice that the transmission axis is vertical. And then after that, before it, you actually have unpolarized light. This portion here is unpolarized light. They're all oscillating in various different planes. But because my polarizer here is vertically polarized, it has a vertical transmission axis, you will see that only waves in the vertical direction can pass through. That's what you're seeing here. Okay, this entire thing is polarized light after passing through your first polarizer, which has vertical transmission axis. Okay, now this one is your second polarizer. All right. Okay. So notice what happens when I try to change the angle of the second polarizer. Okay, right now, when the polarizer is at an angle of 0 degrees, meaning to say the transmission axis is perfectly vertical, you see that whatever wave you have here is exactly the wave that you have after the polarizer. Notice that the amplitude, I think it's better to see the amplitude. Notice that the amplitude did not change before and after. This means that intensity did not change because intensity is proportional to amplitude squared. You learned this before. So in amplitude before and after did not change, so intensity did not change. Okay, right? So that one you can see from here. But what if I change the angle to 90 degrees? Say now I change it to 90 degrees. All right. So I twist this until it's all the way to 90 degrees. Okay, so you see now, once I twist it all the way to 90 degrees, my transmission axis is now perpendicular to my polarized axis. It's now perpendicular to my polarized light. All right, it's now the transmission axis is now perpendicular to my polarized light. There's nothing that passes through. You see, amplitude here is 0. Therefore, intensity is 0, consistent with what you just saw inside the notes. Okay, now what if I'm now at a different angle between 0 and 90? Okay, so let's look at what happens here. If I am at a different angle, sorry, I just deleted it. Okay, but never mind. So back to this one. If my angle is a different value, neither 0 or 90, maybe now I change it to 45. This is what you get, right? Okay, notice what happens to the amplitude. This one, the amplitude is here. But then this one, the amplitude is here. The amplitude for this one is actually less than before, right? Amplitude is less, therefore intensity should be less also. But at the same time, you see, although the transmission axis here is diagonal, whereas this one, the polarized light, is vertical, it doesn't mean that none of the polarized light can pass through. The polarized light will still pass through following the direction of the transmission axis, just that your amplitude is now less, your intensity is less. Okay, so this is the common thing that people somehow got confused along the way. In your case like this, if your transmission axis is diagonal, your wave will still pass through. It will still pass through and it will oscillate in the direction of transmission axis, just that the intensity is less, the amplitude is less. It will only really ever be 0 if you have it at 90 degrees, when your transmission axis is perpendicular to your polarized light. In this case, it is 0. At any other directions, no. Okay, so that is for this.